Thank you. Okay, so using seismic ambient noise to map South Australia's crust. All right, so in the traditional sense, passive seismology refers to the use of earthquakes to probe the structure of the earth. And then we've got a particular sub-branch, seismic tomography, refers to illuminating a particular volume, seismic energy from all possible directions, and we can build up a three-dimensional picture. So it's akin to a giant CAT scan. So here, this is a tomography slice. It's developed using a type of seismic wave called a Rayleigh wave. A Rayleigh wave with a period of 3.5 seconds. And to properly digest that, we need to understand two things about Rayleigh waves. So first of all, they're a type of surface wave. So these are waves which are traveling laterally close to or near the surface of the earth. And secondly, their depth of penetration depends on their frequency. So the lower the frequency, the deeper they travel within the earth. So what depth interval is a Rayleigh wave with a period of 3.5 seconds sensitive to? As a simple intuitive rule to guide understanding, we can equate period in seconds to depth in kilometers. Better still, we can think of a peak sensitivity, about 3.5 kilometers depth, and diminishing on either side of that, according to something like a bell curve. So to the map itself, these are Rayleigh waves. They're crisscrossing South Australia. The blue colors represent areas where the waves are traveling relatively faster, and the red colors represent areas where the wave has been slowed. Okay, so what do we see? At this depth, the main change in elastic property of the rock that the wave is sensitive to, it's going to be the contrast between crystalline basement and sediment. So if we look at the northern margin of the model, the waves are being slowed as they encounter the sediments of the Lake Eyre and Eromanga basins, although punctuated by the Peak and Denison inliers to the west of Lake Eyre. We also see reduced wave speed zones coincident with the location of Lake Torrens, Lake Frome, some more subtle signatures in the vicinity of Olympic Dam and Carrapateena on the Stuart Shelf. And then if we head east, we see these big signatures coincident with the Bancania Trough, the Renmark Trough, flanking the Curnamona province. Now, the power of surface waves is that we can look in different frequency bands and effectively step deeper into the earth. So this is a similar tomography slice, except this time at a period of 15 seconds. So we can think of that as 15 kilometers, so getting into the mid-crust. And evidently the patterns have changed. The scale bar in the top right-hand corner is also much reduced. So we're talking now about more subtle lithological changes in the mid-crust. So from a mineral systems perspective, many of the major mines, they sit on the edges of these zones of reduced wave speed. So for example, Turkula, Olympic Dam, Carrapateena, and we can work our way all the way across to Broken Hill. And so that begs the question, are we actually seeing the deep footprint of these mineral systems in the crust? And the obvious corollary from that is, are the margins of these red blobs, are they potentially prospective areas that we should be giving our attention to? Stepping forward again, or deeper rather, so this is a tomography slice developed at a period of 22 seconds. Again, the pattern continues to morph, and we again see this power of surface waves to step deeper into the earth. We again see this coincidence between the location of many of the mines and the margins of these zones of reduced wave speed. But this time I'm going to draw your attention to Western New South Wales, and this large trending high velocity band, the blue band, trending northeast, southwest through Broken Hill. Might we there be seeing the signature of a relict arc? So it's through these three tomography slices that I'm demonstrating, or hoping to demonstrate, the power of passive seismology. We've got, we effectively have a proxy for sediment thickness or depth of basement, albeit at a resolution that's dictated by quite a sparse station spacing. In the mid-crust, we're potentially seeing the signature of or the deep signature of mineral systems. And here we have an example of potentially seeing a regional scale tectonics. Now, the kicker to all this is that all these models were developed using not earthquakes, but seismic ambient noise, an example of what is shown in the top left-hand corner. So this is the ever-present background chatter that's apparent in all seismograms. It's seismology's white noise. So that begs the question, first of all, how, and secondly, why? So why use ambient noise above earthquakes? And to explain that, I'm going to take a step back and we'll have a closer look at surface waves. So when an earthquake happens, we get two classes of seismic waves that are generated. Body waves, which plunge through the deep interior of the Earth, and surface waves, which roll along the surface. A real example of this is shown in the top right-hand corner. This was a seismogram recorded here in South Australia back in 2007. It's a Rayleigh wave caused by a large earthquake offshore New Zealand. Now, all I do as a seismic tomographer, and really 90% of seismology, can be condensed into the expressions on the bottom. So I measure the travel time of waves between points. So if you're operating at the plate scale, that could be between New Zealand and the station in South Australia. But what I do, it's between stations in South Australia. So I measure that time, I know the distance, and that gives me a wave speed. And that's our window into the geology. And again, the power of surface waves, I just look at different frequencies. So I don't get a single measurement of wave speed between 2 points. I get a suite of them, and they encode the structure of the Earth at different depths. And I can see that explicitly by looking at this particular surface wave in a variety of frequency bands. So that's shown on the right-hand side. And I've color-coded those green and gray at the top. Again, all I want for my measurements is a nice, simple waveform. And within the blue corridor, I have that. So this is a snapshot at a particular location. If I could track those wavelets in real time, they'd look something like the animation on the lower left, easily measurable. That's not the case in the gray at the top. So at these higher frequencies or shorter periods, these waveforms are very complex. And the fact is, I can't extract anything from them. They're not amenable to measurements. So what I'd really need, or rather I should say why, it's because those higher frequencies have traveled in the crust. They traveled for a long distance in the crust. In that case, it was between New Zealand and here. And there's a lot more compositional heterogeneity in the crust. Every interaction those wavelets have, it becomes imprinted on them. And it renders them very complex by the time they get here. It's not that they traveled in the crust per se, it's that they traveled a long distance in the crust. If I had a large earthquake offshore, it would solve my problems, but we don't. Or do we? I'm going to make the case that, in a sense, we do. These earthquakes have just been hiding in plain sight in the seismic ambient noise. So now I'm going to step through the alchemy that allows me to convert this stuff into earthquakes. So to that end, imagine, if you will, that I did have large earthquakes offshore South Australia. So I'm going to start the clock at time 0, at which your earthquake happened. 200 seconds later, it turns up at imaginary station U in South Australia. 400 seconds after that, it turns up at imaginary station V in Queensland. So there's a time difference of 400 seconds between them. I can use a signal processing technique called cross-correlation to find both the signal and the time lag between them. So it's a sliding multiplication, a sliding dot product, and it returns any similar signals in the time series and the time lag between them. And I want to imagine shrinking the size of these earthquakes progressively. The cross-correlation function on each case is shown on the bottom. And I'm going to shrink them to such an extent that these earthquakes, they become hidden in the background noise, in the true background noise. So I'm going to refer to local noise. That could be a tree swaying near one of these seismic stations. And we reach a point where we can't really see anything. We can see the peak at 400 seconds in the cross correlation function. It's no longer a dominant peak because all the other randomness is added into it and generated random spikes. And that's the end of the road for our earthquake story. But the ocean, believe it or not, is a source of seismic energy. So all that heaving swell offshore on our continental shelf, a portion of that energy gets transmitted through the seabed where it continues on as seismic energy. And the key difference relative to our earthquake example is that the ocean is always on. So you could imagine repeating this cross-correlation process for successive time segments. And at each point, I will have the very weak signal at a time lag of 400 seconds. The next thing I'm going to do is I'm going to form a cumulative sum of each of these cross-correlation functions. So the true randomness should begin to cancel out. And at each point, through constructive interference, I bolster the signal at 400 seconds. I can fast forward this whole process to indicate that the more time series I have available to perform this procedure, the better the signal that emerges. Now here's a real-life example of that, so getting back to South Australian seismology. On the top right-hand corner is that cumulative sum cross-correlation function. This was using seismic ambient noise from two stations, so one on the Eyre Peninsula, one near Broken Hill. This is about 5 or 6 years of continuous data that went into generating that cumulative sum. And the key point is that if I look at that in different frequency bands, so I get these nice wavelets at precisely the frequencies that the actual earthquakes let us down. So ambient noise is the creation of virtual earthquakes locally here, such that the energy doesn't have the baggage of a long transit in the crust before it gets here, and they lend themselves to measurement at frequencies that constrain crustal structure. So again, all I do, I look at this in different frequency bands. For example, these stations are separated by about 609 kilometers. The travel time of that particular wavelet is about 190 seconds, and that gives me a wave speed of about 3.2 kilometers per second. And that's all it gives me. It doesn't tell me any of the details of the wave speed variations along that path. It's one average. And it's only through the combination, or rather doing that for all the station pairs that happen to be recording at the same time, that we can build up this compendium of average wave speeds. So this is at a period of 3.5 seconds. Again, the blues represent faster wave speed, the reds slower. And even in that, we can see to first order the geology of South Australia. So the Gawler Craton crystalline basement versus the slower wave speeds of the Eromanga Basin or the Murray sediments to the east. And the tomography step is really solving all those constraints simultaneously. So I get back to this point. So really, I'm essentially a smooth map of sediment thickness of South Australia. And then I repeat in different frequency bands. So again, getting into the mid-crust and seeing what are potentially the deep footprint of mineral systems. Now, of course, this is only possible because we have seismic stations. So this is a map of seismic stations past and present that contributed to this work as it stands today. So these are mostly driven by ANU and Geoscience Australia, stretching right back to the mid-90s. But latterly, the survey here has gotten in the act with the deployment of a 38-station broadband array across the eastern central Gawler Craton. And above that to the north, we have our partner Lake Eyre Basin array. So I service these stations at 6-month intervals. I'm currently working on the latest batch. But credit to the team at ANU as well. So this is AusPass, the Australian Passive Seismic Server. They're making lots of legacy data sets available. These are rolling off the conveyor belt all the time. So this will allow me to expand the footprint of this work into the southern Delamerian and the southeast corner of the state. This is but one aspect of the work, this noise tomography of the crust. So I'll do the same, except using actual earthquakes for the lithospheric mantle, using body waves, a different type of wave, to add granular detail. And then I've got my partners at ANU who are throwing different techniques at these data sets. Shubham is doing his PhD under Caroline. And the end product will be a unified seismic model of South Australia. And I'll finish just by thanking all the different people and bodies who have made this possible. So instrument from the Ozscope and Geoscience Australia instrument pools, the computational heavy lifting of GADI at the NCI, traditional owners, pastoralists, our liaison called Telfer at the Woomera Range Complex. 2 of our stations are in the red zone, and all the people who have helped me with the field work. With a special mention to Bruce Golby, who did so much of the organizing early on. Thank you.